Hello everyone, it's time for tutorial number 3 of Math 2000. My name is Brian and I will be your tutor for today. So today your instructor has asked me to go through 3 questions, so let's jump right in. Question 1. Let S be a compact subset of Rn and let x naught be a fixed point inside Rn. Does there exist a point y inside the set S such that the distance from y to x naught is less than or equal to the distance from S to x naught for all possible S and S? So more simply, your instructor is asking, prove that there exists a closest point in S to x naught. And furthermore, is this point necessarily unique? So let's do it. So consider f, the domain of f is S, and the codomain is the real values. We define it like this. So in other words, this is an alternate way of writing it. F of S is equal to S minus x naught for all S and S. So we consider this function, and the first thing we observe about this function is that it's continuous. So why is it continuous? So let Sn converge to S inside the domain. So these are all values inside S. Then we note that f of Sn and f of S, what's their distance in the image? That's just equal to Sn minus x naught minus x minus x naught. And by the reverse triangle inequality from a previous assignment, that's just Sn minus S. So we were told Sn is converging to S, and then by the reverse triangle inequality, the distances in the image is getting even smaller. So in other words, if Sn converges to S in the domain, then f of Sn converges to f of S inside the real line. And that's obviously as n goes to infinity. So what we've shown is that f preserves limits. F preserves limits. So in other words, that's the same thing as saying as f is continuous. So far what we've done is that I've defined a function f. This function f is continuous. S, we are told, is a compact set. So from lecture, you would have learned about the extreme value theorem. So let's use that now. So recall S is compact. Compact. So then, by the extreme value theorem, f attains its max and min. And right now we'll put emphasis on the minimum. F attains its minimum. So what does it mean to attain its minimum? So in particular, there exists a point in the domain such that f of y will be less than or equal to f of S for all possible S and S. That's what a minimum is. So if I just simplify this expression, what's f of y? F of y is just y minus x naught. And that's less than or equal to S minus x naught. So then we're done. Because we have now shown that y, well, we have literally shown that. So there's a point y inside S that is closest to x naught. So I could say for all S and S. So therefore, y is the point in S that is closest to x naught. So that's part one. Part two is asking, is y unique? And the answer here is not necessarily. So in general, y need not be unique. And I'll give you an example. So here's an example. Let S be the unit sphere inside R2. So that's x squared plus y squared equals 1. And quite obviously the unit sphere is compact. It's closed and bounded. Okay? And let's consider the origin. And I will notate the origin as x naught. X naught equal to 0, 0. Is there a point that's closest to the origin? Well, again, we're working with the unit circle. You can draw better. Okay? This is a circle. And the origin is 0, 0. And S is the unit sphere. So everything inside S has a distance of 1 to 0, 0. So quite trivially in this example, all points are the points of minimum distance to 0, 0. So in this example, so trivially, in this example, S minus x naught will be equal to 1 for all S inside S. So therefore, all S inside S are of minimum distance to the origin x naught, or minimum distance to x naught. And this is just a cooked up example. Sometimes the point of minimum is unique, sometimes it's not. And in this example, it's not. And that's it for question 1.